My name is Adel Gastli. I'm going to present to you the second part of the gate drive circuit. In this part, I'm going to present the bipolar junction transistor BJT-based drive circuits. Bipolar junction transistor BJT is driven and controlled by its base current. For an NPN transistor, to turn and keep it on, we need to flow a current between the base and emitter. To turn and keep it off, we need to cancel this base current and set it to 0. A typical base current waveform is shown in this figure. This waveform can control the BJT's turn on and turn off times in order to make the transistor commutate very fast and thus obtain fast switching speed. The transistor turns on time T-on can be reduced by allowing the base current to peak during turn on, resulting in low forced gain beta F at the beginning of the transition. After turn on, the forward gain beta F can be increased to sufficiently high value to maintain the transistor in its quasi-saturation region. The turn-off time can be reduced by reversing the base current and allowing base current peaking during turn-off. Increasing the reverse base current IB2 decreases the storage time. The commonly used techniques for optimizing the base drive currents are turn-on control, turn-off control, proportional base control, anti-saturation control. We're going to see these types of controls in the next few slides. During the switching on transition of the transistor, the base drive source voltage VB goes high to a positive value V1. The capacitor C1 is initially discharged, so it draws a large base current. The base current reaches instantaneously its peak value IB1, which is limited by the resistance R1. Capacitor C1 continues to charge through the resistances R1 and R2 until the capacitor is fully charged and the base current flows through R1 and R2 only. So the final steady state current is IBS, which is the saturated base current. So this is what is called turn-on control. When the capacitor C1 becomes fully charged, its terminal voltage VC1 becomes nearly equal to V1 multiplied by the ratio R1 over R1 plus R2. The capacitor charging time is determined by tau1, which is equal to C1 multiplied by the product of R1, R2 and divided by the sum of R1 and R2. The capacitor charges through the equivalent resistance, parallel resistance of R1 and R2. When BP becomes 0 at time T1, the base emitter junctions becomes reverse biased. So C1 discharged through R2 and the maximum reverse base current is IB2, which is equal to the capacitor charge voltage VC1 divided by its parallel resistance R2. So here R2 limits the peak base current value when VB changes to 0. Afterward, the base current decreases while the capacitor is discharging until it reaches 0 and then the switch turns completely off. The capacitor discharging time constant tau2 is equal to the product of R2 and C1, which is a bit larger than tau1. This slide summarizes what happens during turn on and turn off transitions. During turn on, the capacitor C1 charges through R1 and R2 with a time constant tau1. So the base current peaks at a value IB1 and then this decreases with a time constant tau1 until it reaches its steady state saturation value IBS, which keeps the transistor on for some time. That's the on state period. During turn off, the capacitor C1 discharges through resistance R2 with a time constant tau2 until it reaches zero value, and then the transistor turns off and stays off. Usually to allow sufficient charging and discharging times, the circuit designers allow an on-control pulse width T1 of a minimum of 5 times the capacitor C1 charging time constant tau1. Similarly, for the off time, the width T2 must be minimum of 5 times the capacitor discharging time constant tau2. The minimum time period that should be set to allow the transistor to turn on and off simultaneously is therefore Tmin, which is equal to the sum T1 plus T2. That's the minimum period that will allow the transistor at least to turn on and then turn off without even a small time on period. Thus, the maximum switching frequency of the BJT is determined by the ratio of the sum of the time constants divided by 5 or multiplied by 0.2 as shown in this equation. As seen earlier, we have concentrated mainly on designing the circuit for shaping the base current for the transistor's turn-on transition mainly. However, it is essential to improve the turn-off characteristic of the switch by controlling the negative peak of the current and shape it in a proper way. To allow high negative peak, it is desirable to apply negative base voltage during the turn-off process. So when VB becomes negative at minus V2, the base emitter junction becomes reverse biased and the capacitor C1 discharges through the resistance R2. The gate emitter voltage VBE is then equal negative the sum VC plus V2, forcing the switch to close very fast. As C1 discharges, reverse voltage is reduced to steady state value of minus V2. So up to now, we have seen that we can control the turn-on time and turn-off time using the same circuit. However, in some circumstances, if different turn-on and turn-off characteristics are required, a turn-off circuit using C2, R2, and R4, as shown in this figure, should be added and designed separately with different specifications. This circuit gives us the freedom to select different values of the capacitor and the resistance for each control circuit, the turn-on and turn-off circuits. You can notice here that the diode D1 isolates the forward bias drive circuit from the reverse base drive circuit during turn-off. This means that C1 and R2 are used during turn-on transition only. Now let's see another type of base current control, which is called the proportional control. This type of control has advantages over the constant drive control because it allows the base current value to adapt to changing collector current. In other words, if the collector current changes due to changes in the load demand, for example, the base drive current is changed in proportion to the collector current. Let's see how can we implement this technique by considering the following circuit. Notice that we need a 3-winding pulse transformer, and we need also an additional switch and one capacitor C1 and resistance R1 that are connected in series with the additional switch and the tertiary winding of the pulse transformer. Let us consider the instant when switch S1 is closed while the source voltage VB is at high level V1. At this moment, a pulse current will flow in the capacitor C1 and resistance R1 and tertiary winding entry of the transformer. Therefore, a pulse is induced in the primary winding N1 of the transformer. This current flows through the base and emitter of transistor Q1, which makes the switch Q1 turn on to saturation. Therefore, the collector current starts flowing into the transistor and the secondary winding N2 of the transformer. When load current, which is also the collector current, changes, similar change will be induced in the base current through transformer action. This will add more base current through induction action between windings N2 and N1. Therefore, transistor Q1 would latch on itself and S1 can be turned off. So the base current varies proportionally to the load current. That is why we call it proportional control. The proportion gain is determined by the transformer ratio N1 over N2. So the transformer ratio is equal to the collector and base current ratio, which is actually the gain beta of the transistor. For proper operation of this circuit, the magnetizing current, which must be smaller than the collector current, should be as small as possible. And switch S1 can be implemented by a small signal transistor, and an additional circuitry is necessary to discharge C1 and to reset the transformer core during turn off of the power transistor. This makes the circuit more complex and expensive. Next, we'll see how anti-saturation control can be realized. Let's first recall the BGT characteristic of the collector emitter voltage VCE versus base current IB shown here. We have a cutoff region in which the transistor is closed and the voltage VCE is at maximum value. Then the active region is the linear region where the voltage VCE is proportional to the base current. And finally, the saturation region where the voltage VCE saturates and does not decrease further even when the transistor is driven hard. It means that when IB becomes higher and bigger. Now, the region just between the saturation active region is called soft region, and the transistor is said to be driven soft. However, if the transistor is driven hard, the storage time, which is proportional to the base current, increases and the switching speed is therefore reduced. The storage time can be reduced by operating the transistor in soft saturation instead of hard saturation. This can be accomplished by clamping the collector emitter voltage to a predetermined value, as shown in this figure, which we will analyze further in the next slides. In this case, the collector current is given by this equation, where VCC is the load source voltage, RC is the load resistance, and VCM is the collector clamping voltage. Note that the collector clamping voltage VCM must be larger than the saturated collector voltage so that the transistor can be driven soft. Now let's understand how this collector clamping circuit operates. Without the clamping, when the BGT is off, diode D2 is reverse biased and it is in blocking mode. So when VB, which is the base voltage, is high, diode D1 is forward biased, which turns on. In this situation, the resulting base current IB equals I1 and is adequate to drive the transistor hard, then transistor turns on. Recall that the collector current is related to the base current with the gain beta. After the collector current IC rises, the transistor turns on, which brings the collector emitter voltage VCE to its saturation level. The diode D2 becomes forward biased and conducts. Thus, clamping takes place. So according to Kirchhoff voltage law in this loop, VCE is equal to the base emitter voltage plus the voltage drop across the diode D1 minus the voltage drop across diode D2. Now, considering the load current equation, which is obtained by Kirchhoff law in the load loop, and replacing VCE by its value in this equation, it is possible to rewrite the load current equation as follows. Now, knowing the collector current is related to the base current by the gain beta, we can obtain the relation of the collector current with the load current and base drive current I1 drawn through the base source. According to Kirchhoff voltage law, in the loop shown in the red color here, we can write that the voltage drop across the diode D1 is equal to the sum of the voltage drop across diode D2 plus the voltage drop across the collector and base terminals of the transistor. This equation can be rearranged by writing VCV is equal VD1 minus VD2. For clamping to take place, VCB must be positive, which means that VD1 must be bigger than VD2. This can be accomplished by connecting 2 or more diodes in place of D1. That will result in a higher load voltage drop inside the series connection of the diodes in D1, more than the voltage drop that is in one diode VD2. Also, the load resistance RC should satisfy the following equation, where beta IB is equal IC is equal IL plus I2, and this should be bigger than IL. So beta IB must be larger than IL, which is the load current. Now, using the previous equation of the load current that we have displayed in the previous slide, we can obtain the following equation that must be satisfied for the clamping to take place. So clamping action results in a reduced collector current and almost elimination of storage time. At the same time, a fast turn on is accomplished. However, due to increased value of VCE, a little bit in the soft region, the on-state power loss is increased, whereas the switching power losses is decreased. So it's a compromise between switching losses and on-state losses. Now, let us study one example to illustrate the clamping effect. In this example, we have a base drive circuit similar to the one we have seen earlier, with a load voltage VCC equal 100 volt, load resistance RC equal 1.5 ohms. The voltage drop across diode D1 is 2.1 volt, and this voltage can be made or obtained by 3 diodes connected in series. The voltage drop across the diode D2 is 0.9 volt. The base drive voltage VB is 15 volts. The base emitter voltage VBE is 0.7 volt. The base drive resistance RB is 2.5 ohm. And finally, the transistor gain beta for this situation is equal to 16. So in this situation, we would like to calculate the collector current without clamping, the collector emitter voltage, VCE, then the collector current with clamping. Let's first see what happens before clamping takes place. As seen earlier, without clamping, the base current would be calculated using the equation we have seen earlier and would be found equal to 4.88 amps. Of course, this value of the current will drive the transistor hard. Now, for this value of IB, and if clamping does not take place, the corresponding collector current would be IC equal beta times IB, and that is 78.8 amps. However, because of the clamping circuit, the collector emitter voltage will be higher than its saturation voltage and will be equal to 1.9 volts as calculated here. The load current can be calculated using this equation, which gives IL equal 65.4 amps. The collector current can be determined also from the previously seen equations, or obtained equations, and would be equal to 66.15 amps as shown in this equation. From these obtained results, one can easily notice that the collector current is larger than the load current, but smaller than its value 78.08 that was obtained without the clamping as seen above. So the key points to retain from this section of the BJT drive circuits are: a BJT is a current controlled device. Positively peaking base current can reduce the turn on time, and reversing the base current peaking can reduce the turn off time. The storage time of a BJT increases with the amount of base drive current, therefore overdrive should be avoided. This is the end of this part. Thank you for your attention. Please join us in the next part.